Hello, welcome to Digital Electronics. Today's lesson, we're going to be learning how to simplify equations using Boolean algebra, specifically for electronic circuits. Now, Boolean algebra was developed in the 1800s by a man named George Boole. He came up with several rules that we are going to use to simplify equation. Let's begin by listing those rules. Now, I'm going to number them so that we can refer to them as I work through some examples. The first rule had to do with ANDing a circuit, a switch, with a zero. Let's call this rule number one. When you AND a switch with a zero, for example, you have an AND gate and any signal X, it doesn't have to be a switch, I guess. It could be any signal coming from anywhere, like it could be a bigger circuit that feeds into that. But if the bottom circuit is always ground or just a signal that's zero, the result is always going to be zero because the AND gate will never have both inputs equal to 1. Therefore, the result of this first rule is always 0. The second rule that was published was any signal ANDed with a 1. And again, you have an AND gate. If you have any signal X with a 1, the result is going to depend on whatever X is. So the answer for that one is X. 3, we're going to have X ANDed with the same signal X. So that's basically when you have a signal going into an AND gate and also going to the other leg of the AND gate. As you can see, if X is 0 or X is 1, the output is just going to follow X. So just X. The next rule, rule number 4, is if you have X ANDed with its opposite. So here you have two opposites. Now you're going to have an AND gate where if X is 1, not X, you can think about it as having an inverter right there. The opposite, it's always going to be a 1 0 or a 0 1. So they're never going to be 1, both of them. So the output of the AND gate is never going to have the same 1 on both, so it's never going to be a 1. So therefore, it's always going to be a 0. Let's do now the same thing, but with OR. I'll write it over here on the right. Let's call that rule number 5. We're going to have X or 0. Number 6 is going to be X or 1. Number 7, X or X. And number 8, X or not X. So now we got to think about an OR gate. An OR gate, remember the way it works is that as long as there's 1 1 at the input, the output's going to be 1. So for this first one on number 5, we have X or a 0. Well, the output is going to depend on X because the bottom signal is never going to be anything other than a 0. So if X is a 1, the output's a 1. If X is a 0, the output's a 0. So the answer to 5 simplifies to just whatever X is. Now, however, for number 6, if the bottom signal is a 1, then X doesn't really matter. Whatever signal's coming to the other input of the OR gate, it could be a very complex equation. It could be X, I just called it X, but it can be any signal. The bottom signal, if it's 1, it doesn't matter what X is. So you have for sure, a 1 in there. So it's always going to be on. This 1 is just going to pass right through. Okay, now rule number 7 says that if you have X on both inputs, so that one, I think it's obvious that the output is just going to follow X because if it's 0, the output's 0. If it's 1, the output's going to be a 1. So it just follows it. This last one on this row is if we have opposites. So if X is going to the top and then we invert it going to the bottom input, there's always going to be opposites. If X is a 1, the input over here is going to be a 0. And there's going to be a 1 at the output. If X is 0, its opposite is a 1, and it's still going to be a 1 at the output. So no matter what, for opposites, the output's always going to be a 1. Now, there's a couple more rules that I'll list. one of them, it's actually called the consensus. Actually, no, hold on. Let me do rule number 9. I guess if you have x with a double inverter, so like if you have a signal coming in, inverted, and then inverted again. So no matter what it is, here it's going to be flipped and then it's going to be flipped back, which is just X, the original one. So if you have two, like a double inverter, you just replace it and take it out with, replace it with a wire. Okay. Rule number 10, actually it's several rules. They're called the consensus theorems. If you have a signal ORed with its opposite, but the opposite has other things, let's call B. It doesn't matter what it is, it's other things. Or it could be not A or not A with not B. Like it doesn't matter what it is ANDed with, excuse me. You could also have not A or A, they're opposites, and this one has something else, or not A or A, not B. The thing to pay attention here is that these are all called the consensus theorems, by the way. What you should notice is that you have a letter ORed with its opposite, and then there's something else attached to the opposite. Same thing here. These are opposites, and there's something attached to the opposite. There's always opposites. One is alone, one is a term by itself, the other one has something else next to it. So again, opposites right there. One is alone and one has things attached to it. So what we're going to do is I'm going to tell you this. This is like a little shortcut that I learned from one of my students. These are all called the consensus theorems, like I said. What happens is the variable that's alone stays behind, or the variable that is with something else goes away. One of my students said to me, it's like they're enemies. So like the person that's alone is the good person, and the person that has hostages is the bad person. They're opposite. The good person and the bad person are opposites. And so what you do is you get rid of the bad person. Like in the movies, you always destroy the bad guy. So here, the bad guy is this one because it's holding hostages and you don't want them to do anything to the hostages. So the bad guy goes away and it just becomes B. So on that side. So on the second one, for example, the good guy is alone, the bad guy is the opposite of the good guy, and the bad guy has hostages. So we get rid of the bad guy, which is the not A, and we're left with that letter. The next one, the good guy is alone, so we keep them. The bad guy is the opposite of the good guy and has hostages, so that's A, so get rid of A, and we're left with B. And the last one, the good guy is alone, so the good guy stays. The bad guy is the opposite of the good guy, which is A, and then we get rid of that one, and the not B stays. Like I said, you could summarize this. These are all the consensus theorems. You could summarize this by just saying, if you have anything, I'm going to call it X. I guess I started using A's and B's. I apologize for that. But if you have X, or let's say W, R, P, Q, not X. The good guy is alone, which is this one. The bad guy is the opposite, which is this one. And the opposite has hostages, which are those. So you just get rid of the bad guy. So this just becomes like that. So hopefully that makes sense. That was one of my students who gave me that idea of the good guy and the bad guy. So that's the consensus theorem summary. Okay, so those are all the rules that we're going to be using. You should also know that the properties apply. So we know the commutative property. The commutative property says that I can AND A and B, and it's the same thing as saying B and A. So if you have an AND gate, it doesn't matter if I put A at the top or B at the top, it's going to give me the same result. And it's the same thing for OR. So if I have A or B, is the same thing as saying B or A. The other rule that you should be aware of is, this is an algebraic rule also, is the associative property. The associative property says that I can AND A, B, and C, and that's the same thing as ANDing A and B first and then C. So like if you need a triple AND gate, but you only have two, you can AND the signals like this. So A, B, C, or you could do the B and C first. So it doesn't matter which ones you AND first, the result, the logic is still going to be the same. And the same thing for OR. So if I say A or B, C is the same thing. And, oh, no, it's never, it's the same thing OR. And it's the same thing if you have multiple, like if you have D, E, like it doesn't matter how many you have, the order in which you group them first, it doesn't matter. It doesn't affect the result. And lastly, the distributive property. The distributive property says that if you have ANDs and ORs together, like if you have A and B or A and C, you could say it as A and B or C. So in algebra class, or yeah, it's the same. It's still algebra. It's just with logic rather than with numbers. In algebra, you've seen this as multiplying that across like that, and you get the result. The other distributive property is when you have a product of sums. So if you have, oh, I guess I'm doing this one backwards, but it doesn't matter. So if you have A or B, and then C or D, let's say. So what you're going to have to do is the FOIL method, where you multiply the first letters. So that would be AC, or AND them. I shouldn't say multiply, but it's kind of like multiplying. So A and C, that's the first, and then there's the outer ones. So that would be ORed with A and D, and then the inner ones, and that is OR BC, and then the last. So it's first, inner, outer, last, the FOIL method. And then the last one we get OR BD. So that's how you apply the FOIL method in Boolean algebra. It's the same situation, except you don't, like if you have A and A, you don't write A squared, you just write A, and then you use property number 3 or rule number 3 to know that that's just 1A. I just realized I used rule number 10, the consensus theorems. I just wrote them all using A's and B's instead of X's, but it's the same. You could use any letters for these situations. Same thing with the commutative associative properties. Okay, so these are the rules that you need to know in order to be able to simplify equations. So let me work out a couple of examples. I'm going to make these rules a little smaller right there so I can refer to them, and I'm going to put them right here on the left, and I'm going to work out problem on the right here. So let's work on example 1. So example 1, I'm going to use, I use ABC. So ABC, let's say we have an equation that has an inverter on B, or we have ABC that has an inverter on A and as well another inverter on B, or ABC and it has an inverter on A alone. Okay, so let's say we have that example, and I should say, like this is a function, whatever the function is, right? F equals, or the output turns on whenever those 3 minterms are on. I mean, remember, this is assuming you have already seen the design process and you know that after the truth table, you know to extract the minterm equation. And let's say there's 3 minterms, and this is what you have. So what we want to do, instead of building the circuit, if we were to build a circuit at this time, we would have, let's see, I'm going to use a bright color. We would have 1, 2, 3, 4, 5, 6 AND gates, right? Every time you multiply, or every time you have a dot or the multiplication symbol, that's an AND gate. So that's 6 AND gates, 1, 2 OR gates, and 1, 2, 3, 4 inverters. Unless you reuse some of them, which you could, but let's just pretend we're using all of them. So that's 2, 4, 6, 7, 8, 9, 10, 11, 12 gates. So we're going to use 12 logic gates if we did not simplify at this time, if we were to implement the circuit like this. So let's use Boolean algebra to simplify this equation to see if we can make the circuit implementation better and easier for us, more efficient, less components. So whenever you approach a Boolean problem, what you do is it's a repetitive process, so like a recursive process. You look at the equation and see if you see any of the rules. Now the rules can be summarized into 4 things to look for. Okay, so the first thing to look for is see if you see a 0, because if you see a 0 in the equation, you know you can use rule 1 or number 5, right? So look for zeros. The other thing to look for is look for ones. If there's a 1 in the equation somewhere, you can use rule 2 or you can use rule 6. The other thing to look for is look for doubles. If you have doubles of something either anded or ored, you know it's going to, it's going to simplify. Now, the other thing to look for is look for opposites. If you have opposites anded or opposites ored, you know it's going to simplify. And I think this one, number 9, is pretty easy to spot. If you see a double inversion, like it's like, oh, something's going on there, you can cancel it. And then you can think of these, the consensus theorems, you can think of as opposites, where again, one is alone and the other one has hostages. So that's what you got to look for. Let me summarize it. Look for zeros, look for ones, look for doubles, look for opposites, and then look to see if you see opposites, one alone and one with the bad guy. And this one will stand out by itself. You don't have to worry about that one so much because it'll be like in your face. Okay, so let's look at example 1 again. Here, do I see a 0? No. A 1? No. Do I see doubles? Well, I see an A, not A here, and a not A here, but that's not the same because doubles means that the same thing just twice. Like this one has other stuff next to it, so that doesn't count as a double. Do I see opposites? Again, I do see opposites, but they're not opposites like here where they're alone. Opposites, this one, they all have other stuff, but okay, so does that mean they're opposites like in the consensus theorem? Well, for the consensus theorem to work, one has to be alone. And so no, because like there's an A and then there's a not A with hostages, but A is not alone. So that doesn't work. Remember, for the consensus theorems, you have to have one letter by itself or one term by itself and then the same exact term opposite with hostages. So no, at this point, I cannot apply any of the rules 1 through 10. Okay, so the next thing to do is to rearrange things. And more than likely, you're going to have to use the distributive property, where right here, you take a letter that is in common with multiple terms and you take it outside of the parentheses. And what's going to be left in the parentheses, you're going to apply rule 1 through 10. So here, let's look to see if I have things in common. Now, I have, in this case, let me highlight some of the options. I can take out A is in common with this one and that one, right? That's one option. Another option is that I have, let's see, I have C in all of them. Another option is I have not B anded with C on this too, but not on the last one. I also have not a positive C on this one and that one. Okay, so there are many options as to which ones I can factor out using the distributive property. I'm going to tell you that I have had a lot more success and it's simpler and the simplification happens faster if instead of taking out one letter like the orange one, like C, from multiple places, that's not better. What's better is, I mean, sometimes that's the only option, right? But if you have 2 letters like the purple, where you have not BC from 2 terms, that's going to yield a better result, more than likely. So again, if you have a choice of factoring out 1 letter versus 2 or 3 letters, factor out more letters. So in this case, what we're going to do is we're going to factor out what I've underlined in purple. So let me erase all these other options and So we're going to factor out not B and C from these two terms. Okay, so we're going to follow the distributive property, and so we're going to take not B and C outside of the parentheses, and I'm only taking it out of these first two terms. So this third term, I don't touch it. I just write it again in the next row, the next line. So again, I took it out of two places, so inside of my parentheses, I'm going to have two things. Okay, so from this first term, if I take B and C out, I have to put inside of the parentheses, what do I have to AND this one with to get the original? So basically, what's left over if you take not B, C out? So the answer for the first one is A, right? And then from the second term, if I take not B, C out, what is left is the not A. All right, so hopefully we did that one right. Again, what we did is we used the distributive property to take something that was in common with these two terms. All right, we're in a new line, so we repeat the process. Rule 1 through 10. Do you see a 0? No. Do you see a 1? No. Do you see the doubles? No, I don't. Do you see opposites? Yes, I see opposites right here. I see that these two are opposites. So I'm going to use, I guess, rule number 4 or rule number 8, one of those. Well, rule number 4 is opposites ANDed or multiplied, and rule number 8 is opposites ORed or added. So as you can see, I'm going to have to use rule number 8. I'll write it here, I guess, if it helps a little bit. Following rule number 8, if I have opposites through an OR gate, the answer is going to always be 1. So I can replace everything in parentheses with just a 1. So not BC, and I could put parentheses like that. I could just get rid. Those are two extras, so I'm just going to put and a 1, or the other one on the side that I haven't touched. The term just comes down from the top row. Okay, we're in a new line, so we start the process again. Okay, do I see a 0? No. Do I see a 1? Yes, I see a 1. I see a 1 right there, right? Actually, you could treat it as just C and a 1, or you can treat as not be C and a 1. It doesn't matter. Any signal. Again, we're going to be using either rule 2 or 6, and you can see it's ANDed, so it's rule number 2. So if you have an AND gate, this could be a whole mess of things coming from anywhere else. And a 1. This signal can be other AND gates, etc. Let's just call that. In this case, it would be not be C the result, but it still becomes one signal. So I guess you could treat this whole thing as just the same thing as X in our formula. A way to think about it is that if you have anything ANDed with a 1, the 1 goes away and everything else stays. So in this case, again, using rule number 2, we're gonna the 1 just goes away and it depends on the remaining signal. So now we're in a new line. So here we start the process again. Do you see a 0? No. Do you see a 1? No. Do you see doubles? The same thing twice. No. Do you see opposites? No. There's no opposites. There's like the not B and the B, but again, they're not alone. There's no one that's alone. Okay. So so at this point, I cannot apply a rule 1 through 10. So let's look at the properties, and 99% of the time, it's a distributive property. So let's see if we have something in common. I'm running different colors. Oh, I'll use yellow, I guess. What we have in common here is, I think I made a mistake. Did I forget to bring down an inverter from somewhere? Let me double check. Not B, A, and then A, not B, C, not A, not A. No, I think it's still right. Not B, C, not B, C. Okay, I think it's all right. All right, so if you can see from here, at this point, I was just double checking because sometimes I forget to bring an inverter or something, and then it changes my equation completely. So as you can see from here, I am left with B's are not the same. The C. There, I didn't see it at first. Okay, so then the C's are in common. So what I'm going to do is I'm going to use, again, the distributive property, and I'm going to take a letter outside of the parentheses. And this is the only choice I have. I cannot take out B because it doesn't exist on the not B. Okay, so here we go. We're going to take C outside of the parentheses. From this first term, I'm left with not B. And from the right-hand side term, I am left with not A and it with B. All right, so at this point, we have the uh, the the new line. So we have to check the rules again. So rule 1 through 10. Do you see a 0? No. Do you see a 1? No. Do you see the doubles? No. Do you see opposites? Well, yeah, the B and the not B, but not quite. But one is alone. So see, this one, the not B is alone. So it's not quite this one's. It's actually the consensus theorems because the B is alone. This one is alone. And the other one, they're opposites. And this one has hostages. So what we're going to do is we're going to use one of these consensus theorems, which I think happens to be this one, where you have a letter ORed with its opposite, and the opposite has, again, it sounds silly, but it's like, it's the good guy, the bad guy is opposite, and the bad guy has hostages. So you just destroy the bad guy. In this case, this one is the one that's the bad guy because it's the one that has hostages. So I'm going to rewrite the equation one last time without the bad guy. And that's what it becomes. Now, at this point, there is, I don't think there's anything else I could do. Let me see. Is there a 0? No. Is there a 1? No. Is there doubles? No. Is there opposites? No. Nope. There is no rule I can apply at this time. Can I apply any of the properties to change things? Well, this one is, again, this is going to be your choice. I could use the distributive property and actually multiply things out or distribute. So this would be C not B or C not A. You could do that. However, you will find that there is actually more gates if you distribute. So one thing to point out here, let me get a red dot. So here, if I count the gates on this one, it's going to be 1 AND gate, 1 OR gate, and 2 inverters. So that's 3 gates, which is equal to 3 chips, right? Or 3 ICs. If you started breadboarding, you know that there are several several gates per IC. For this one right here, I have 1 AND gate, 2 AND gates, 1 OR gate, and 2 inverters. So that's 2, 3, 4, 5. This one is 5 gates. Wait, I didn't count right. It's 1, 2, 3, 4 gates. The top one is 4 gates, but it's still 3 ICs. Okay, so 4 gates, 3 ICs, and the bottom one is 1, 2, 3, 4, 5 gates. But it's still 3 ICs. But either way, if you have the same number of chips, but one of them uses less gates, that means it's going to use less wires. So actually, I would probably choose this as the most simplified equation. However, sometimes textbooks have things where they say, well, leave your answer in sum of products form. Well, if that's the case, then this one you need to, that's the sum of products, sum of products form, because you leave it as multiplications and then you add them. So, but again, I think the point of Boolean is to simplify as much as possible. So I would say that the 4 gates is the most efficient one. All right. Now, for those of you that have looked at other type of simplification, there is another person who published some algebraic simplification, and that is De Morgan. So there was another man who published two rules, De Morgan's theorems. I guess it's not technically Boolean, but it's kind of put together because it wasn't George Boole, it was another person who published it, but it's used for the same purpose or very similar purpose. And what Mr. De Morgan published was that if you have a signal that is inverter, so if you have A inverted ORed with another signal that's inverted, that would be the same as ANDing them first and then inverting the result. So basically, instead of using individual inverters at the input of the gates, you can put one inverter at the output, but you have to change the logic from AND to OR or vice versa. So that's the same thing. If you have an inverter on a signal and then an inverter and another signal, and then you AND them, that's the same thing as taking the signals, ORing them, and then putting the inverter after. Okay, so with that, there could be other things that you could do. For example, I'll take this even further, and the simplest equation right here, I could use De Morgan's and say, okay, so my result was not B or not A. And you could put an alphabetical order if it's bothering you. Sometimes I can see that can be a little bit like disturbing to be like, just put them in alphabetical order. It doesn't really matter because of the commutative property, right? Okay, so at this point, you could use De Morgan's and say, all right, instead of inverting each signal and then ORing them, I could just take both signals and AND them first. I guess I'll change the order. And then invert the result. So you could do that, and that would use less gates, actually less ICs altogether. So now let me get rid of the parentheses. So that would be A, B with an inverter, and then I'll just put the C after. Again, it doesn't matter. So now it's totally in alphabetical order. So now check this out. This one right here, if you use De Morgan's theorems as well as Boolean, now I only have 2 AND gates and 1 inverter. So this one uses 2 ICs. So it uses 2 AND gates, 1 inverters. So that is 3 gates right here that we're using, which is equal to 2 ICs. So definitely, if you have a choice between just using Boolean algebra or adding De Morgan's theorems, you should try to see if you could use De Morgan's theorems as well, and it's going to simplify equations a lot more. All right, there's lots of other examples you could look at, but I think this example went through most of the rules. All right, I hope that was helpful, and I will see you next time. Bye-bye for now. I'm done, sweetie. I was finishing recording a lesson. How are you? Bye, you too, sweetie.